All right, we have talked about radicals and some of their properties in your homework last class. You got lots of different questions to deal with on those radicals and what they do, but now we're going to, or their exponents rather, but now we're going to look also at radicals and how we can go between the two and how we can work with each of them. So we have Tia and Tahani. And they know that a to the m over nth power is the same thing as the nth root of a raised to the nth power. They're wondering which form, radical or exponential, is best to work with when using numerical and algebraic expressions. Tia says she prefers radicals since she understands the following properties, and there aren't too many to remember. So if n is a positive integer greater than 1 and both a and b are positive real numbers, then we have these properties. The nth root of a to the nth is a. Those just cancel off. Here's another property. The nth root of a times b is the same thing as if we split those two up as the nth root of a times the nth root of b. Now, note that this is multiplication in both cases. It must be multiplication. We cannot do that over addition. Then the third one is also the nth root of a divided by b can be split up similar to how we split up the multiplication. We can have the nth root of a divided by the nth root of b. Tahani, though, says that she prefers exponents since she understands the following properties and there are more to work with. She says when you multiply two bases, a, with different exponents, m and n, you add those exponents. So a to the m times a to the n equals a to the m plus n. And then if you were to raise one exponent to another exponent, you multiply them. And similar to radicals, if you have two factors being multiplied, you can raise each of those to the same power. So a times b to the n is the same as a to the n times b to the n. Same thing for division. A over b to the n power is the same as a to the n power over b to the n power. And finally, if you have these last two, if you have two bases divided by one another with differing powers, you subtract the power from the numerator by the power in the denominator. And it's important to say that a does not equal 0. That is because if we have a equals 0 and this denominator is 0, we have an undefined number, and we cannot have an undefined number. It doesn't exist. So we cannot have a being 0. That's also true for this next one right here, a to the negative n power. That gives us a denominator of a to the n, or 1 over a to the n. I think it's important to note also, like if we had 1 over b to the negative n, it reciprocates the fraction. So that would also bring the b to the numerator. That would make it b to the n power. Okay, so I just want you guys to note that this can go that way or that way. It just makes a reciprocal for that fraction. So good things to note. Now, this page right here is going to be a great resource for us as we are looking at different properties of radicals and exponents, both in the lessons and in homework. So as you're getting familiar and comfortable with these properties of radicals, properties of exponents, please feel free to come back to this page and refer to it to help you on your homework. Okay, this is now what we will do. Do this. We're going to illustrate with examples and explain using the properties of radicals and exponents why this right here are true identities. So basically what we're looking at is if you have 1 over the 1 over nth power, let's look back up here and see if there are any of these properties that will help us out. There aren't a whole lot up there. But basically what we can say is, okay, if I take, let's see, if I were to raise, here's a way I could look at it. If I were to raise each of these to the nth power, like this, I would have a to the 1n over n. When I raise a power to a power, I multiply those, and I get a times a to the 1 over n times n. Now, when I raise something that's having the root of it, or something that's being rooted and I raise it to the same power as that root, those things cancel off. Similar, I would have a to the n over n, which is just a to the first. So I get a to the first is equal to a. A to the first is just the same thing as a also. So that's one way I could think about that. I'm going to do the exact same thing actually over on this other side. A to the m over n is equal to the nth root of a raised to the m power. Now, if I were to raise each of these to the nth power again, those cancel. This cancels with that one, and I would get a to the m is equal to a to the m. If I wanted to take it one step further, I could also say I'm going to take the mth root of both of these, boo boo, boo boo, and I get a is equal to a. Okay, so there are two ways that I could state using those properties that these are true identities, right? But now, using their preferred notation, we're going to simplify radicals. So Tia would simplify the cubed root of 8x to the 8th as this follows. So she separates it out. She looks at what is my root, and then she separates this out into exponents that are the same as that root. Why? Well, let's look at this. Using the multiplication properties, also notice this, right? We've got 3 plus 3 plus 2, that equals 8. So that's how we were able to separate this out into its factors. And the reason we separated it out into those cubes is because when you take the root of something that has the same exponent, those exponents and the roots cancel off. So we are left with x times the cubed root of x squared, right? So just like this, x times the cubed root of x squared. We can simplify when you multiply something by itself, it's just that thing squared. And then we have times the cubed root of x squared also. So this would be our solution. So she found cubes because we were taking the cubed root, okay? Also, Tahani points out that Tia also used some exponent rules in her work. Yeah, okay, great. Thank you for that, Tahani. We appreciate your input. But now let's look at how Tahani would simplify hers. So on hers, she would actually make this fraction, or she would make this a fractional exponent where she brings the radical into the denominator of the exponential fraction. And then she separates it out into a mixed number. And knowing that when you have exponents added together, you can separate it out in terms of a multiplication statement. So x to the 2 plus 2/3 is the same thing as x squared times x to the 2/3 power. So 8/3 became 2 2/3. And then we were able to say x squared times x to the 2/3 power. Or what she did is she went ahead and brought this back outside of the radical. The denominator of the fraction comes outside of a radical, and we have the cubed root of x squared. So this is the final answer. We should note they both came up with the same final answer, even though they used different approaches, right? So we are going to do the same thing with a couple of our own expressions. So this one right here, we've got the square root of 27. The first thing we need to do is get this into its prime factors. So we will go through prime factorization. This has factors of 3 and 9 and 3 and 3. So another way I could represent this, another way to represent 27 is 3 cubed, because 3 cubed is equal to 27. So I could actually set this up like this. All right. Now the trick is, okay, what is my radical? What is my root? And if there's nothing written there, then I always assume, because it's a square root, I assume it is a 2. So what I need to do is I need to get these exponents in terms of squares, or 2's, so that I can cancel them off with the square root. So I'll have the square root of 3 squared times 3 to the first, or just 3. I don't need to include that 3 to the first because I know that 3 to the first is just 3. But once I have these two based on the properties of radicals, I can separate this out into the square root of 3 squared times the square root of 3. Remember, I'm not writing that one because 3 to the first is just 3. Now I can see, those two cancel off, and I get 3 times the square root of 3. So that is my answer right there. Okay, for Tahani's method now, we're going to still start with the square root of 3 cubed. But now we want to take this and make it an improper fraction in the exponent. So remember, that is an implied 2, so it'll be 3 to the 3/2 power. And remember that she went from an improper fraction to a mixed number, which if we make this a mixed number, there is 1 2/2 in there, which makes 3 to the first plus there's still 1/2 left over. Okay, and then when I have exponents that are added, that means I can take two bases and multiply them together, being 3 to the first times 3 to the 1/2 power. Remember, if it's just to the first, it goes away because 3 to the first power is just 3. And I can say 3 times 3 to the 1/2 power. And when I have that denominator in the exponential fraction, I can bring that out outside of the radical. So I have 3 to the square root of 3, or 3 times the square root of 3. I didn't write a 2 up here because it's implied, remember, in that square root. So again, we got the same answer, just to note, right? All of these, even though they're different methods, we should be getting the same answer. Okay, the next one, first thing we need to tackle is trying to find the prime factors of this 32 right here. So we'll go ahead and do, let's see, 2 and 16, 2 and 8. Oh, even numbers are nice. 2 and 4, and 2 and 2. Okay, so I see a whole bunch of 2's here now that we're all in the prime factorization. So I'll just go ahead and write those as 2 to the 5th, and I'm taking the cubed root of this. So Tia's method rather, she separates it out into exponents that match our radical number. So we need to separate it out in terms of cubes. So we have the cubed root of, I see 2 cubed times 2 squared. So I can separate these out because when I multiply them together, I would add the exponents and it would give me 2 to the 5th, right? So breaking them down, I can just make sure that they add up to 5. And as long as they do, I'm good to go. Now, I can separate these out into their own radicals. So I'll say the cubed root of 2 cubed times the cubed root of 2 squared. I did that cube intentionally right here because pew, pew, they cancel off. So I get 2 times the cubed root of 2 squared. Just like that. Okay? Yeah, I think that is enough to go on. I can leave it just as simple as that. All right, this next one, we've already done the prime factorization, so I'll do 2 to the 5th, the cubed root of 2 to the 5th. What Tehani's method is she takes that radical and puts it in the denominator of a fraction in the exponent. So we've got 2 to the 5/3. There's an improper fraction, but Tehani then makes it a mixed number by saying this is 2 to the 1 and 2/3. And then because those exponents are added, I can separate them out by saying 2 to the first power times 2 to the 2/3 power. So note that when exponents are being added, their bases are multiplied, right? We've talked about that a couple of times now, so now it's time to remember that, okay? Then finally, I have this exponential fraction where I need to pull the denominator outside of a radical, and I will have 2 times the cubed root of 2 squared. Remember also this 1, 2 to the first power is just 2, so I don't need to write that, okay? When we look, we see they both got the exact same thing again, which is good. All right, here's another one. Now we're going to introduce a coefficient and a variable. So remember, the multiplication rule says if we have 2 things that are multiplied inside of a radical, we could pull them out just like this. Oop, not a squared. That's a 7th. Wow. So I want you to be aware of that, right? So we're not going to do that just yet, but we can do that very, very soon. The first thing that we'll need to do is still take the prime factors of 20. Even numbers are nice, 2 times 5. And then we'll need to separate this out when we put it into their own, or when we're looking at separating that out, we need to separate that out in terms of squares because this is the square root. So, simplified, I have 2 squared times 5 times x to the 7th, okay? Now I want to separate everything out into squares. Well, I have 2 squared already separated out, which is real nice, but I'll leave that there for just for now. So 2 squared times 5 times x squared times x squared. That would be x to the 4th total times x squared. That's x to the 6th total, but I need x to the 7th. So I have to have all of those exponents of the x add up to this 7 right here. But now I'm good. So because of that multiplication rule, remember what I said up here just a second ago and then promptly erased. But when I have multiplication inside of a radical, I can separate it out. So I have the square root of 2 squared times the square root of 5 times the square root of x squared times the square root of x squared times the square root of x squared times the square root of x. Okay, now I have a whole lot of things that cancel off. Pew, 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 pew. Right, so outside of these radicals now, I'm going to also bring all of these to the front. In front of this root 5 because it's easier then to see what is exactly under that radical instead of wondering, oh, is this x under a radical with that 5 or is it outside of the radical? So I'm going to bring all of those out here just like that. So 2 times x times x times x times the square root of 5 times the square root of x. Now, if I was able to separate these things out, I can do the reverse. So I can actually put these both under the same radical because that radical is has the same number outside of it. It's both the square root for those. And I have x times x times x, which is just x cubed. So I'll have 2x cubed root 5x. Okay, so that's how I can both expand a radical this way and make the radical a little bit more succinct by putting two different values, two different terms that are under a square root into the same square root, right? Now let's look at Tahani's method. So we'll start again with this 2 squared times 5 times x to the 7th, but Tahani would actually separate it out into those exponential fractions. So remember, she can put this in the denominator of each of these exponential fractions. So we'll have x to the 2 over 2, no, not x, I'm sorry, 2 to the 2 over 2 times 5 to the 1 over 2, because if there's nothing written there, it's an implied 1, times x to the 7 over 2. That 2 over 2 right here just simplifies immediately down to 2 to the first power, which is just 2, times 5 to the 1/2 power. But now we've got 7 halves, so we need to separate that out as a mixed number, which should be 3 plus 1/2. And then we can separate that out further. If exponents are being added, that means we can multiply their bases. So we've got x to the 3rd times x to the 1/2. And now I have 2 whole number exponents and 2 fractional exponents. So I should pair those together with whole number exponents together and fractional exponents together. Now, if they both have the same denominator, I can put them under the same radical with that value as the radical. So it's 2x cubed square times the square root of 5x. So notice now also, I want to be really careful. This cube is belonging to the x, not to this radical here, okay? That radical is just a 2. So I might even make it more specific and say this is a square root so that I don't get confused as to where that 3 belongs, okay? But that's a good thing to note up here as well. But you can see we have the same value. Okay, now it's Tia's method on this one that's a little bit more complex. Oh my goodness, it has a fraction bar in it. Holy smokes. Remember though, if we refer back to that first page, we can deal with fractions just like that. We can deal with fractions just like that, okay? So we shouldn't see that and shiver. We should see that and be confident in all of our abilities, okay? It's also a cubed root. That's just a good thing for us to know. Now, as well, what we'll do is I see x's in the numerator of this fraction and in the denominator of this fraction. Same with y's. So I'll go ahead and simplify those first. I have x to the 1st up here and to the 7th minus, or up down there. This x will cancel off with one of these x's, so I have 6 left. Now I have 5 y's up here and 2 y's down there. 2 of those y's will cancel off with 2 of the y's up here, and there will be 3 left. So notice how that is, the exponents are additive. Over to the side as well, I just want to do the prime factorization of 16. Notice I am going all the way down to the prime numbers. I'm not dealing with 16 because I know it has a square root, because actually look at this, it's the cubed root, not the square root. So if I just imagine, oh, I know what the square root of 16 is, you will be bound for trouble because we need to get it all the way down to the prime factors before we simplify. Okay, that's just a word of caution there. Okay, now we can set up this square root again, or this cubed root rather again, where we have 2 to the 4th power times just y cubed in the numerator over x to the 6th power. So Tia's method has been, let's get in terms of our radical first, and then let's try to simplify. So I need to set that 2 to the 4th in terms of cubes. So I'm going to go 2 cubed times 2, and then times y cubed, which actually is already in terms of a cube, and then times x cubed, or over x cubed times x cubed, because that x to the 6th breaks up into 2 cubes, right? So now I can, over multiplication, separate out all those cubed roots. So the cubed root of, I'm going to need that to be smaller, 2 cubed times the cubed root of 2 times the cubed root of y cubed. Now I have a division bar. But remember our rules, I can do the same thing over division. So it's the cubed root of x cubed times the cubed root of x cubed. Okay? Anything that I've set up to make it so that the cubes cancel, right? I've done that intentionally. Let's go ahead and cancel them. Boop, 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 boop. All right, we've got a whole bunch of cancellation. So I've got 2 times the cubed root of 2 times y. Ooh, I should bring that up to the front. I'll bring that up to the front on the next time I write this down. All over x times x. So when I simplify, I'll bring that y out to the front so I can see that it's 2y outside of the radical times the cubed root of 2 all over, when I simplify x times x, it is x squared. Okay? It looked daunting, but it's really not so bad. Now let's look at Tahani's method. So I've already got this simplified version up here, so I'm going to pull that down as well so that I don't have to re-simplify. And I've got the cubed root of 2 to the 4th times y cubed all over x to the 6th. Now remember, Tahani takes this and makes it a fractional exponent, and she can do that to everything in the numerator and the denominator. So I will have 2 to the 4 thirds times y to the 3 thirds all over x to the 6 thirds. And now I need to take these improper fractions and make them mixed numbers, and I need to take anything that can be just divided out and simplify that. So I've got 2 to the 1 and 1/3, or 1 plus 1/3, not 1/2, times y to the 3 over 3 is just 1, over x to the 6 over 3 is just 2. Now, because I have addition in the exponent, I can use multiplication for the bases. So I've got 2 to the 1st times 2 to the 1/3 power times y all over x squared. When I simplify that one step further, I have to take this fractional exponent, bring it out outside the radical. I want to move this y over to the front so I don't have to wonder if that is inside of a radical or not. And I will have 2y times the cubed root of 2 all over x squared. And check it out once again. It is the exact same thing as we got previously, right? Awesome. Okay, Tia and Tahani continue to use their preferred notation when solving equations. So now we have two sides of an equal sign that we have to solve. So the opposite of a cube is a cubed root. So we just go ahead and do that. Beep, beep. They cancel. Once that 27 is simplified, it cancels, and then we've got a pretty easy equation to solve here, an algebraic equation. Tahani would do this a similar thing, raising it to the 1/3 power instead. Okay, so we're just going to do the same thing with Tahani and Tia, but using it over equations as well. So I see x minus 2 quantity squared equals 50, and I'm going to need to square root both sides. It's easy on the left, just boo boo. Also, remember when I square root, I need to insert a plus or minus. Now I have plus or minus 50, and that's not a perfect square. So let's simplify that radical by going ahead and separating this out into its prime factors, all the way down to its prime factors, which are 2, 5, and 5. So I will rewrite that. I've got x minus 2 equals plus or minus the square root of 2 times 5 squared. I can separate those out into their own radicals, and I can say x minus 2 is equal to plus or minus root 2 times root 5 squared. Boop, boop. Those cancel off, and I have x minus 2 is equal to plus or minus 5 root 2. Notice I'm writing my real or my rational numbers first and then my irrational radicals second. Okay? Then finally, to solve, I will add 2 to both sides and I get x equals 2 plus or minus 5 root 2. Now that is as simplified as we will get. You could put this in your calculator and say, okay, what is 2 plus 5 root 2? And what is 2 minus 5 root 2? But that then we would have to round because that is an irrational number. It will go on forever, the decimal will, and that is actually less exact. So we're going to go ahead and leave it right up here as 2 plus or minus 5 root 2. Okay, Tahani's method now would have x minus 5 quantity squared equals 50, and Tahani would raise this to the 1/2 power, right? Just like she did in the example above. All right, we've already dealt with what this is in terms of its prime factors, so we're just going to put that in. Then I've got x minus 5 raised to the 2 times 1/2, because when I raise one power to another, I just multiply those exponents, is equal to 2 times 5 squared raised to the 1/2. And I'm going to go ahead and distribute that 1/2 to both of those, right? 2 to the 1/2, or 2 times the 1/2 is just equal to 1. So I've got x minus, and that's not 5. I wrote that down poorly. Sorry, you guys. That's x minus 2, x minus 2, and, oh, I'm about to write it over here. X minus 2, woohoo! So then I've got 2 to the 1/2 power times 5 to the 2/2 power, which those are nice anyway. And I get x minus 2 is equal to 2 to the 1/2 times 5, which 2 over 2 is just to the 1, so I'm good. I can simplify that, and I'll add 2 to both sides. So I will do x is equal to 2 plus 5 times the square root of 2, because I took that denominator and pulled it out outside of the radical, right? Okay, this is where we found our first little nuance difference. I do not have a negative sign here. So what that tells me, and this question is actually going to come up a little later, is what that tells me is I need to, when I raise something to the 1/2 power, I need to insert a plus or minus here so that I can actually be true to what the true answer is, right? So if I raise to the 1/2 power, I need to include a plus or minus. All right, let's have a look at Tia's method for this next one. So now we've got some things outside where we're going to actually have to do a little bit of algebra before we just take a square root, because I can't just take a square root of this whole thing. Well, actually I could, if I wanted to, because these are being multiplied. So I've never done that before, but heck, let's try it. So 9 times x minus 3 quantity squared equals 4. So if I go ahead and I take the square root of this entire side and this entire side, first thing I should do is I should get the prime factors of 9 and 4, which, look at that, nice prime factorization. So I can say this is the square root of 3 squared times x minus 3 quantity squared is equal to the square root of 2 squared. And I should also include a plus or minus right there, right? Now when I separate those out, I've got the square root of 3 squared times the square root of x minus 3 quantity squared. Notice that this whole thing is being squared. That's the only way that I'll be able to cancel those off. If it was just x minus 3 and just the 3 was squared or something, I could not use a radical to cancel that squared. Okay. And then I've got plus or minus the square root of 2 squared. Well, those cancel off, these cancel off, and these cancel off. So I am left with 3 times x minus 3, the quantity, is equal to plus or minus 2. Now I can go ahead and simplify using PEMDAS, right? Use the parentheses last, and I've got x minus 3 is equal to plus or minus 2/3. I'll have to add 3 to both sides, and I get x is equal to 3 plus or minus 2/3. Now you could simplify that to make it some mixed numbers if you like. It'll be more exact, so it would be 3 2/3 or 2 1/3. So you could do either one. That is 2 1/3, not 2 to the 1/3 also. But that's what we get. Okay, 2 solutions, right? That plus or minus gives us 2 solutions. Now let's look at Tahani's method. We've got, well, actually, let me just go ahead and say this is 3 squared times x minus 3 quantity squared is equal to 2 squared. Now Tahani's method, she raises this to the 1/2 power. Now we talked about this in the last one. When you raise to the 1/2 power, just like square rooting, we're going to have to include a plus or minus, okay? Then I can split these all out because over multiplication I can split them out. So I've got 3 squared raised to the 1/2 power. When I raise a power to another power, I just multiply. And I've got x minus 3 quantity squared raised to the 1/2 power. When I raise a power to a power, I multiply. And that's equal to 2 squared to the 1 times 1/2, right? To the raise one power to another power, you multiply them. So then I've got this times that times that times that. Those all multiply out to just be 1. So it's 3 times x minus 3 equals, oh, I should include my plus or minus here, 2 plus or minus, right? I will divide both sides by 3, not negative 3, just 3. And I get x minus 3 is equal to plus or minus 2/3. Have to add 3 to both sides, and I get x equals plus or minus, nope, 3 plus or minus 2/3, just like that, okay? Which is the same answer as this one up here, but we didn't separate it out into the plus or minus. All right. Zach now is showing off his new graphing calculator to Tia and Tahani, and he's particularly excited about how his calculator will help him visualize the solutions to equations. Look, Zach says, I treat the equation like a system of 2 equations. I set the expression to the left equal to y1 and the expression to the right equal to y2, and I know the x value where the graphs intersect. The expressions are equal to each other. So he's saying if he sets this equal to y1, and this equal to y2, where those two graphs cross is the correct value, right? That would be these points that we solved for right here, actually. So Zach shows off his new method on both the equations. And to everyone's surprise, both equations have a second solution. We already included that because plus or minus is necessary, right? So what I want you to do is I want you to actually plug those equations in to see both of those solutions. Okay, so you can use Desmos and plug them in so that you can see where they come or where they intersect, where they collide, and that's their solutions. But we're going to say we have to include a plus or minus when we square root, okay? So as we explain that, you'll need to take some time and do that. I'll be checking those notes when I get back to class. But as we take some time to explain that, that's because the square root of 4 could be 2, but the square root of 4 could also be negative 2, right? Because negative 2 times negative 2 is positive 4, just like positive 2 times positive 2 is positive 4. Okay, so they both are viable solutions, and we need to account for both of them. So what we've done already is insert the plus or minus. All right. Good luck on your homework. Remember, you can email me questions if you have them, and I'll go through them with you. Just as a real quick reminder, remember anything in this place, or this place, or A, B, and C respectively, do not include the x with them. So for number 2, for example, A is only 2, B is only 3, C is only 1, okay? Do not include the x with them. That would be incorrect. I will be marking that, all right? So only take the coefficient. All right, should be enough to go. Good luck.